This is Geometry Lesson 5.1, Congruent Figures. So our big idea today says that figures are congruent if and only if they are related by an isometry, which is a reflection, rotation, translation, or glide reflection. So we just finished chapter 4, where we looked at all of these different types of composite reflections. So remember, a composite reflection is just more than one. Okay, it's a combination of reflections. And we figured out that those all turn out to be rotations or translations, glide reflections. Okay, and those are called isometries. And we also talked a lot about the ABCD theorem, which says that every isometry, so every combination of reflections, preserves four things: angle measure, betweenness, collinearity, and distance. We've covered that at length. And now we're going to talk about why isometries are all congruent. So the definition of congruent figures: two figures, f and g, are congruent, written like this. So when you see the little squiggle mark above the equal sign, that's congruent. If and only if, meaning I can read this backwards, g is the image of f under an isometry. So if I have an isometry, I have congruent figures. If I have congruent figures, I have an isometry. Remember, if and only if can be read forward and backwards, the conditional and the converse. So when we see this, it's similar to equals, okay, but it's not an actual measurement. It's just saying this is the same size as this. This has the same angles as this. Everything that we saw here is preserved. So if we look at these three shapes here, these would all be considered congruent. These two are congruent. It's the same size. They have flipped. This is clearly a reflection over a line right here. Okay, but the size of this has not changed. We would say these are congruent. And based on the definition of congruent figures here that was given to us, we would say they are congruent because this is a reflection, and all reflections are congruent. And if I was going from here to here, that's a rotation, right? So from here to here, I'm just spinning it. And so these are also congruent. So if I knew the side length here, I would know the side length here. If I knew the angle here, I would know the angle here. So that's what congruent means. And some other language that we need to understand with this, if we slide down, some more definitions of congruent figures. Two figures are congruent if and only if G is the image of F under a composite of reflections. So we need to know that means the same thing as isometry, composite of reflections. Combination of reflections, that's what isometries are. So two figures f and g are congruent if and only if g is the image of f under a rotation, translation, reflection, or glide reflection, which those are all composite reflections. Those are all isometries. So this is really just hammering the vocabulary, making sure we understand those all mean the same thing. All right. So this is kind of just the intro here in 5.1. So we're just kind of looking at some vocabulary, making sure we understand where we're headed. So because of the definition, another term for an isometry is a congruence transformation. So I just gave you another one. So remember, transformation is any different change in size, shape, location, orientation. You take a shape, something changes. That's a transformation. So a congruence transformation is where it doesn't change size. And to be more specific, it's an isometry where all of your A, B, C, Ds are preserved. So when figures are congruent and they have the same orientation, we're going to call them directly congruent. So two different types of congruence. And then you can see we're also going to look at oppositely congruent. So both of these are shapes that are congruent, same size, but something's different about them, and it has to do with the orientation. So when they have the same orientation, directly congruent, that would be translations or rotations. We spent a lot of time in chapter 4 talking about how orientation is only preserved in translations and rotations, not reflections and glide reflections. So basically, if I can just take the shape and move it over and it's going to match another one like A and B, you can see at the right, A and B are directly congruent because I can take one and just slide it over to the other one. All right, when figures are congruent and have opposite orientations, we would say they're oppositely congruent. Makes sense. Those would be your reflections and your glide reflections. So A and C or B and C are oppositely congruent because the size hasn't changed, the angles haven't changed, none of that has changed, but the orientation has. It's flipped. So I have to flip this shape in order for them to line up, but all of my A, B, C, Ds are preserved. Okay, so directly congruent, translations, rotations, oppositely congruent, reflections, and glide reflections. Let's go to the back. So we haven't studied these too much, just a little bit, but some transformations that do not yield congruent figures would be any type of size change. So we looked at those where we multiply on a graph all the points by a certain size factor. Okay. So that is not going to be a congruent shape when you change the size. That's basically what congruence is the same size. So any change in size is not going to yield congruency. And then this is called a shear, where you can see the shape has just been taken and kind of pushed to the side. The bottom is the same there, and this leans over. And so some things that change on this one, if you think about it, is angles for sure, right? If we think about this as an entire shape or even just the person inside here, as I lean it over here, angles have changed. So therefore, that's not an isometry if the angles have changed. And so then that's not congruent. And you may not see it. You may say, well, the size stayed the same. But if I keep leaning this over and over and over and over, the distance from, say, here to here, keep leaning, keep leaning, keep leaning, that's going to continue to get closer as that line keeps going at a more severe angle. So distance is also messed up here. Angles are messed up, size is messed up. Okay, so this is called a shear. We haven't really talked about those, but those are not congruent figures. Okay, they basically, you have to be able to take one and put it on top of the other and they would match up, even if you have to flip it. But here, that's not going to happen. They are different. So notice there are specific distances and angle measures that have not been preserved. Pretty easy to see that. Okay, so these are not congruent. All right, and then we also, when we were talking about equality, we talked about a couple special properties. We're going to bring those back up. Okay, congruence is going to match equality with these properties. So some of these are just like equality. 3 of those are called the equivalence properties of congruence. So we know the equivalence properties, they hold true for things being congruent. So they're called the equivalence properties of congruence. Just a lot of vocabulary here. So to go back over these, if something is equal to itself or something is congruent to itself, okay, that's the reflexive property of congruence. If we say F is congruent to G, we can flip it and say that G is congruent to F. That's the symmetric property. So if you're just flipping which side things are on, that's symmetric. Same thing on both sides. It's reflexive, just properties we want to memorize. And then the most important one, if F is congruent to G and G is congruent to F, 2 different things, H and F both congruent to G, then we know that F and H are congruent to each other. That's the transitive property. We've used that a lot with equality. It's going to hold true with congruence. And where this starts to come into play is when we're going through proofs and we're writing proofs and we have to give a justification. We're going to use a lot of these properties. So remember, for things to be congruent, it has to be an isometry or a composite of reflections resulting from a rotation, translation, on and on and on. So the reflexive property says anything must be equal to itself. It holds true for congruence. Talk about it right here. How do I represent this property with these figures? So if I reflected F over this line, it would end up over here. And then if I reflected it back, it's right back on top of itself. So after a composite of reflections over line M, F, the original, is going to be congruent to the new shape itself because it's back on top of itself. F is congruent to F. So that's your reflexive property demonstrated through 2 reflections. Okay, symmetric property. If I take F and I reflect it over line L, and then I reflect it again over line M, okay, I could end up at G. So it's possible that if I took F and I reflected it over starting with L, and then I reflected it over G, that could equal G. And the reverse is also true. If I started with G and I reflected it over M, and then I reflected it over L, I'm going to end up back where I started at F. Okay, so F is congruent to G, and G is also congruent to F, shown here, proven through those isometries. And then your transitive property, if I have F, and this would be a glide reflection here, okay, it's going to slide over, and it's going to flip, and I'm over here at G. These are congruent to each other. Okay, the size hasn't changed, the angles haven't changed, just the orientation has changed. And then I can go from G to H as a glide reflection as well. And it ends up over there, and the size hasn't changed, the angles haven't changed. So I could say G is congruent to H again. So I just said F is congruent to G, G is congruent to H. So even if I don't directly relate these two together, although you can see that those right there are looks like a translation, maybe a little bit of a rotation. So you could relate those directly without that middle piece, but the transitive property says I don't need to do that. If I know F is congruent to G through an isometry, and G is congruent to H through an isometry, then I can automatically just jump to the conclusion that F is also going to be congruent to H, and that's our transitive property.